With much frequency, we're led to buy products without asking ourselves what is the physical fundamental behind it. Cars, computers, fridges. One of the most interesting but least described of these inventions is the fan. This invention helped keep us cool during hot times, but contrary to many other inventions, there's little to no study on them. One of the main characteristics it presents is rotational motion.
During this project, we will be determining the rotational motion properties of a fan, including its radial acceleration, its angular velocity and acceleration, as well as the relation of time versus angular velocity and time versus angular acceleration, as well as the process followed to obtain said data.
To determine the rotational motion properties of a fan along its three velocities, including radial acceleration, angular velocity, and angular acceleration.
First of all, once we got our fan, we downloaded the accelerometer app to our iPhone.
We attached the iPhone to one of the blades. We set the accelerometer to measure and started the fan and let it spin for a certain amount of time, then stopped it. We stopped the accelerometer and sent the data to our mails.
We repeated step 2 for the three velocities.
The information obtained from the app was given in the unit G. 1 G is equal to 9.81 meters over square seconds. Since we needed meters over square seconds as a unit in order to find our values, we converted our data to said unit by multiplying it by 9.81. In this way, we found our radial acceleration in these units.
5. We found the angular velocity at a determined point using the formula radial acceleration equals radius times the square of the angular velocity. Therefore, we calculated the square root of the angular acceleration over the radius.
Then we calculated the average angular acceleration by dividing the change of speed over a change of time.
Then, in order to create our graphs, we selected the table containing the values of time and the values of angular velocity and angular acceleration respectively.
The experimental part was done in greens of building number 3 in an outside setting.
The accelerometer was placed 13 centimeters away from the center of the fan. The accelerometer was set to 20 Hz.
Theory and data. We based our experiment on the theory and formulas given to us by Professor Momax in the physics class. According to the lectures, the iPhone's accelerometer helps us calculate the radial acceleration. Radial acceleration is always present in circular motion, and it is responsible for the change in direction. The placement of the phone on the fan blade allowed us to align the y-axis with the radial acceleration. For this reason, the axis used in the experiment is the y-axis.
To obtain the radial acceleration, we used simple conversion factors and formulas in order to obtain other sets of data.
Observing the generated graphs, we found that, even though unregular, the graphs for the angular velocity show that at first, when turning on the fan, there's a growth interval, followed by an interval in which the speed remains more or less constant, keeping its values within a determined range of values, just to be followed by a decrease interval when turning off the fan, leading in this way to the velocity to equal 0.
The maximum speed interval for the first graph is between 13 and 15 radians over second. The growth interval starts at about second 3 and ends at approximately second 6. This tells us that it takes about 3 seconds for our fan to reach its maximum velocity at speed 1. Its decrease interval starts at about second 31 and ends at approximately second 35, lasting around 4 seconds, showing that it takes the fan about 4 seconds to completely stop.
For speed 2, the range of maximum angular velocity is between 14.5 and 17 radians over seconds. The increase interval is from approximately 3 to 6, lasting 3 seconds, and the decrease interval being from 30 to 33, lasting 3 seconds as well.
For speed 3, the range of maximum angular velocity is between 16 and 20, growth interval from 2 to 5, lasting 3 seconds, and decrease interval from 33 to 36, lasting about 3 seconds.
As for the graphs of angular acceleration, we found that, even though irregular, there is a tendency for its values to be around zero at the time when the speed is in this pseudo-constant interval.
Comparing time versus velocity and time versus acceleration graphs, it was found that the angular acceleration increases in around the same interval as the graph of angular velocity. It was also found that as the time was approximating the time when the constant velocity began, there was a decrease in the angular acceleration, keeping its values near zero during said interval.
The irregularities in the graph, the sudden spikes or depressions, are attributed to the fact that, due to the weight of the phone, the fan wasn't spinning regularly and in an okay fashion. Spinning faster at times, slower at others. In fact, the fan was moving so violently that we had to hold it in place in order to do the measurements. Basing ourselves on the obtained graphs, we conclude that for the three velocities of the fan, it takes 3 seconds to reach the maximum speed and 3 seconds to fully stop. We found that the maximum velocity at speed 1 ranges from 13 to 14 radians per second, for speed 2 from 14.5 to 17, and from speed 3 from 16 to 20.
We found that the obtained graphs are consistent with the literature, finding that when the angular velocity is constant, the angular acceleration equals to zero.
As part of our final recommendations, for future characterization of fans, it is recommended to 1. Either using a dedicated accelerometer in order to prevent the shaking and random movement caused in this experiment by the weight of the iPhone. Or 2. When using an iPhone as an accelerometer, making sure that the fan will not be affected by the weight of it.